All right, so we are on chapter 8 and we're going to start in section 1 today. So chapter 8 is all about solutions. So all about mixing different things. And we talked about in the last chapter all the intermolecular forces that determine whether something will dissolve inside of water and all that kind of stuff. And so we're going to practically apply what we learned in the last chapter to some really real life situations and things that you might actually see. So we're going to start out with just kind of defining what a solution is. Then we'll talk about how solutions are made, and then how we can write chemical formulas for those solutions. Then in 4, 5, 6, and 7, these are really the practical applications of that, okay? So we know that solutions are mixtures, and you know that a mixture, when you take two things and you mix them together, you don't chemically change them, right? So making a mixture is a physical change, not a chemical change. So an example of a solution is a cup of coffee, right? You have a cup of coffee, you put in a tablespoon of sugar. When you do that, you're making a homogeneous mixture, which we call a solution. Homogeneous meaning the same. So if you took a little taste of your coffee at the top, now this is after you've stirred it, of course, but if you take a little taste of your coffee in the top, it's going to taste nice and sweet. And then if you take a little taste of your coffee at the bottom, like if you got a straw out, right? That'd kind of be weird, but if you got a little straw out and you were able to taste the coffee at the bottom of your coffee cup, it would still taste just as sweet. And so that's because it is homogeneous. It's a constant composition throughout. So anytime you have a solution, you've taken two things and you've mixed them together. We have scientific names for those two things. We call them the solute and the solvent. So the solute is the one that is in lower concentration, and the solvent is the one that is there in the larger concentration. So a lot of times what we do is we take a substance like sugar and we mix it with water, right? So if I take a tablespoon of sugar and I mix it with a cup of water, which one is in a greater amount? The water is in a greater amount, so that's the solvent. The solute is the one I just put a little bit, so a tablespoon. So that's my solute. My sugar is my solute. So solute is what you put in to the larger container of stuff and you mix it out and it gets evenly dispersed, right? So a lot of times people will call water is and they say this, universal solvent. And it's not always the solvent, but a lot of times it's the solvent. So a lot of times. And the way I kind of remember that is if I draw a water molecule, right? It kind of looks like a V. So solvent, V, looks like a V. Solvent, water is usually your solvent. And so that'll kind of help you remember. So the components don't actually react with one another. They do have some intermolecular forces that will be capitalized upon, but they will not chemically change their structure. So if you take a spoonful of sugar and you put it into water, it's still sugar in the water. It's still sugar water. It's not some new substance, right? So they don't react with one another. But the solute is always going to be the one that's present in smaller amounts. The solvent is always going to be the one present in larger amounts. So here's kind of our example, right? We had our little bit of sugar, our solute, and we put it in the solvent, which was our big glass of water, right? So that's our example. And then we'd stir it and it would become homogeneous. So if you held this up to the light, you would see that it's transparent, right? And the same thing is actually true of coffee. So as long as you don't put anything else in it, if it's just coffee, you can actually see through the liquid. You can see through, and I guess it depends on how thick you like your coffee, but typically coffee is a solution because it's transparent. That's a very, very important quality of a solution, that it's transparent. And so the other important characteristic is that it's not going to spontaneously precipitate out or undissolve over time. Like if you had a bottle of water, you uncapped it, you put your sugar in, You mix it up, you cap it. The sugar is going to stay in solution. And so you could come back a week later and it's still in solution, right? And so it will not undissolve over time. Nothing will settle, none of that kind of stuff. It'll stay distributed evenly. And these are properties that allow us to say this is a solution. So kind of all the things that are really important. You have particles that are very evenly distributed. So it's homogeneous, that's what we say. Right? The components do not chemically react with one another. If you put salt in water, you still have salt water. If you put sugar in water, you still have sugar water. Aqueous solutions. So aqueous meaning water-based. Aqueous is water-based solutions. So LUT solutions. So the solvent, in this case, the solvent is water, are transparent. So if it is where the solvent is water, it is transparent. The components do not separate upon standing. So if you mix like, I don't know, some mud and some water, what would eventually happen? Even if you started up really well, eventually that mud would sink. And so that's not what you see with a solution. So muddy water is not a solution, right? So the components do not separate upon standing, they stay dissolved. And then the concentration can be changed. If we add more or less solvent, we can actually change the concentration of that solution. And we'll talk a lot about that later. All right, so we know that solutions, the common ones that we think of are like water and sugar, salt and sugar, all that kind of stuff. But solutions can be mixtures of gases and mixtures of solids as well. And let's talk about gases first. Air, what we are breathing, is actually a homogeneous mixture of gases. So the air that you breathe is about 80%. Air is about 80% nitrogen N2, right? And it's only about 20% O2, which is really pretty interesting. But it really is a homogeneous mixture of our gases. And so if you were actually to look at this as a solution, and I would say, what is the solvent? You would tell me that my N2 is solvent and my O2 is solute, right? And so this is very common. We actually see this very often where we have mixtures of gases. Mixtures of solids is another thing you've probably come into contact with on a daily basis that you just haven't thought about. Brass is an example here. These are brass keys. So brass is a solution of solids where we've taken metal zinc, heated it, right, and mixed it with hot metal copper. And so you get a uniform distribution throughout. It is not transparent because it's not, the solute is not water, but it's still a solution. And then the other example is you can actually have a mixture of two different states. So here we can have a mixture of water and carbon dioxide, right? A carbonated drink. That's all it is. And so you have water being your solvent, and it's in the liquid phase, and then CO2 is a gas, and it's your solute, okay? So anytime you have a solution where the solvent is water, then we call it an aqueous solution. So that is water. Okay. So water is really, really awesome. We already know that one water molecule can form up to 4 hydrogen bonds with anything that's around it, right? So you have 2 donors. Here's a donor, here's a donor. And then we know we have 2 lone pairs, right? So this is an acceptor, and this is an acceptor. So we can form 4 hydrogen bonds with nearby water molecules. And so because you form so many of these hydrogen bonds, and hydrogen bonds are relatively strong for intermolecular forces, it gives water some really, really cool properties that you don't see in other solvents. So we've already seen that water has a high specific heat, right? So it can hold temperature for a long time, which is really, really important for us, right? Because if it's a hot Louisiana day outside and you don't want all of the water inside of your body to evaporate because it's so hot. So you want it to maintain your constant body temperature. And so you're going to have this nice constant body temperature, even though it's hot outside, because water has a high specific heat capacity. Water also has a very high boiling point because it has lots of strong intermolecular forces. And it also has a low vapor pressure because all those molecules are very, very strong in their interactions with one another. And so it prevents them from escaping into the gaseous form and then creating that pressure on the surface of the liquid. And so high boiling point, low vapor pressure. Remember, they're inversely related. And the really amazing thing that we all take for granted on a daily basis is that solid water floats on liquid water. This is one of the only substances where this happens. So when water freezes, the optimal configuration for water in a solid state, the water molecules kind of space out so that they can make optimal hydrogen bonding contacts and basically kind of stay in that position. When they're in water, they can kind of get close together and change their hydrogen bonding partners and stuff like that. But once they get stuck in that solid, in that frozen state, they're stuck. They can't go anywhere. And so they have to make those optimal hydrogen bondings and stay there. And so they end up a little farther apart. And so because they're farther apart, ice has a lower density than liquid water. So if ice is less dense, the molecules are more spaced out than liquid water, where those water molecules are closer together but moving, then ice will float on water. And this is really, really unique because it's the only, I thought they had a picture in here, but if you look in your book, it's kind of cool. This is the only substance that does that. In your book, they have a picture of, they took some olive oil and they froze some olive oil and then put it in a glass of liquid olive oil and it sinks to the bottom, right? And that's how most substances work. But water, we all know, your ice floats in your glass. So it's really cool. We just kind of take it for advantage. All right, so identify the solute and the solvent of the two components given in the mixtures below. Remember, solvent is there in higher concentrations. So you have more solvent than solute. So a teaspoon of honey is in a cup of tea. A teaspoon of honey is my solute. My cup of hot tea is my solvent. A pack of sweetener is added to a cup of coffee. So my pack of sweetener is again the solute, and my cup of coffee is the solvent. A small amount of anesthetic nitrous oxide mixes with air during a patient's surgery. So my nitrous oxide here is the solute, and then my air, really 80% N2, is my solvent. Okay, so just always look for which one's less, which one's more. So there are some other things that can happen when you mix substances together, and they're not solutions. They are colloids or suspensions. So if you take, for example, milk. Milk is a liquid, right? So it's got water in it, but it's not transparent. You can't see through your milk. So it's not a solution. So we know inside of milk, we have proteins and we have fats inside of them that just don't dissolve. They don't have the properties required to mix with the water, and so they don't dissolve. So homogenized, which means that it's been mixed, are colloids because the proteins and the fats don't dissolve. They're distributed, but they don't dissolve. So the particle size are small enough that they don't settle. So if you take your milk out of your refrigerator, right? If you've left it in the fridge for a couple of days and it hasn't soured, because it's a different thing going on. If you take it out, you don't have to shake your milk, right? It's still homogenized. It's still all mixed. And so because the particle sizes are small, between 1 and 1,000 nanometers in diameter, then the particles are going to still remain suspended in solution. So it's never going to settle. A suspension is something different. A suspension is something that will settle. So suspension, so here's a suspension, will settle. Okay, so muddy water, that's what we were talking about before, will separate upon standing, right? And why? The reason is because the size of the particles are large enough that it will be subject to gravity and it will get pulled down, right? Blood's a good example of another suspension. We know that when we take blood, right, from someone, it's all red. But then if you just leave it on the counter for long enough, what's going to happen is that you have plasma, which is mostly water, and then you have cells. And so if you allow it to settle, those cells are big enough that they will sink to the bottom. And you can actually speed that process up by putting it into a centrifuge and spinning it really, really fast. And that will help to speed the process up, and the heavier things will go to the bottom. The heavier things are the cells. And so the picture is an actual vial of blood. And so you can see down here, these are the red blood cells. And then this is the plasma, which is mostly water. Mostly water, not all water, but mostly water. Okay, so let's go do some problems. All right, so here are our in-class problems. And so remember, your little things to write down are that your solute is the substance being dissolved, so S-T-A-N, being dissolved, and you have a small amount of it. Then your solvent, V, solvent, usually H2O, not always, but usually. So we kind of remember that it's water, right? But present in large amount, right? So one thing that's kind of important to remember when we talk about water being the universal solvent, right? You have to remember that most organic substances are non-polar. So substances, most, we'll say most, not all, but most organic substances are non-polar. Well, like dissolves like. So if water's polar and most organic substances are non-polar, guess what? They don't dissolve. They don't dissolve in water. So you just have to be careful about that and just remember that like dissolves like. So always go back to that, right? Okay, so identify the solute and the solvent in the solutions composed of the following. A cleaning solution containing a tablespoon of vinegar and a cup of water. So I have a tablespoon of vinegar, I have a cup of water. My tablespoon of vinegar is in lower amount, so that's the solute. The cup of water is the solvent, okay? A 3-gallon gas tank is filled with natural gas methane and a small amount of methyl mercaptan, which gives an odor should any gases leak, okay? So that's why natural gas stinks. They actually, you don't actually smell it. And so they put something in it to make sure that it does, so that you can smell a gas leak. Otherwise, it would be completely undetectable before it was lethal. So the majority is our methane, right? So this is our solute, S-O-L-U-T-E, yep. And then our methyl mercaptan is our oh no, I'm doing the wrong thing. Whoa, y'all. My larger thing is my natural gas methane. And so that is the S-O-L-V, solvent. And then my mercaptan ethanol, we're only putting in a little bit of it. So this is the solute, okay? All right, a kilo bar of 18-karat rose gold that contains 750 grams of gold, 220 grams of copper, and 30 grams of silver. So here you're given 3 things. So what you do is you find the one that is the most. The one that is the most, that's our gold, right? Our gold is going to be our solvent with a V. The other 2 substances, both the copper and the silver, are both solutes, okay? So if you have more than 2, right? You're gonna have 1 solvent and the rest are gonna be solutes. Okay, identify the following as solutions or colloids. How are we gonna remember solutions and colloids? Remember that a solution, do a different color, a solution is transparent. That's how you can tell the difference between a solution and a colloid. Solution is going to be transparent. Okay, seltzer water. Seltzer water, completely see-through, so this is a solution. Yogurt. Can you see through yogurt? No, you cannot. So it is a colloid. Salt water. If you mix salt and you get salt water, you can see through it. So it is a solution. Okay. All right. That's it. Have a great day.